Okay, we are going. So, new section for today. Oh, real quick, I'll go ahead and point out while I'm thinking about it. Don't forget, even though today, the stuff that we're going to cover today is not fair game for the exam, right? This is all documented on the class schedule, right? Nevertheless, it is part of the course material, and it you guys okay? Okay. It is stuff that's going to be fair game for the third midterm, and the third midterm is actually not that far away, right? We're basically in November already, right? And the last exam is going to be in early December, so very close. So anyway, for whatever that's worth. So we're going to start. This is section 5.6. We're going to talk about some applications. First, let's talk about averaging. Y'all know how to average numbers, old news. You add, you divide by the count. Let's real quick. Okay. Then I've averaged 6 numbers here. But there is a point of view that says I've averaged 3 numbers. And the numbers are 4, 7, and 8. But I double counted 4 and I triple counted 8. Right? So representing that, now this is all of the exact same calculation really, but just kind of collecting terms together in a way that makes it a little bit more transparent what I've double counted and what I've triple counted, you might say. Right? So you can kind of generalize this by way of this formula right here, with the idea being that whatever you're going to double count, we're going to call that a weight of 2, because it's like it's there twice. It weighs twice as much because it's literally there twice. And so we're going to call this a weight of 2, and the 8 has a weight of 3. And you can see how the weights show up in the general expression. And so the numbers that I'm averaging, those numbers that you're averaging, they show up like so. Right? And so we can just generalize this whole idea of kind of double counting and triple counting with a formula that looks like this. This is called a weighted average. What's one of the really nice things about writing it like this is that now I don't have to restrict my attention to integer number of counts, right? This is a double count, this is a triple count. Well, I could have these weights be any numbers, whatever. The bigger the number, the more weight that it has in the average. Okay. All right, so this is a useful concept, weighted average. Y'all are going to notice, of course, that this is relevant to how grades are computed in this class, right? So the grades are going to be computed as a weighted average. All the details, of course, are on the course website and the class website between the two of them. Some of the details are instructor chosen and some of them are course wide. Anyway, how do these weighted averages work? Well, just like this formula right here. And in particular, remember we've described somewhere what the weights are for our weighted average. In this scenario I've described here, the weights are a little bit different. I didn't want the numbers to get too weird, right? So the 3% weight that we have for something I've already forgotten, I didn't want that to deal with annoying numbers. So those weights, though, we just go right here. Wrong. Oh my gosh, wrong color. Sorry. The weights in green here go like so. And the numbers that we're averaging, well, the grades that we're averaging, again, following the formula above, and Bob's weighted average is computed by this arithmetic. Right? The weighted average per that formula, and it turns out to be this. Does everybody see how I implemented that generalized idea there? Right? Okay. So weighted average, Bob gets a B, by the way. So don't forget that back to our course, right, that there are bins. Right, the registrar will not let me submit a course grade of 2.964. That's not how the Duke grading system works. So I've got bins to take weighted averages and convert them into letter grades. And the big idea is he gets a B because 3.0 is in the center of a particular bin that this number is inside of. 3.0 is your standard B. Okay, so while we're on this topic, I'll say just one last thing, and then we'll go on to the next topic, and that is if you might feel that you don't really have a completely crisp understanding of how grades are computed in this course, just come talk to me. I'll be very happy to clarify. I want to make sure everybody understands perfectly clearly what the grading system is and how all that works. So just come talk to me in office hours sometime. We'll take all the time you need to make sure it all sinks in. Okay. All right. So you can apply this idea of a weighted average to averaging the values of a function. And this is a kind of an aggressive idea if you really think about it. If you look at the values of a function, well, there are infinitely many values of the function, right? There's a value of the function for every real number between A and B. How do you add up infinitely many things, right? It doesn't even really make any sense. So the big idea here is to take the above formula for a weighted average. I've already forgotten what color. Yeah, here we go. The above formula for a weighted average kind of adapted now to an integral setting. Notice we're doing integrals instead of adding. That kind of gets around the whole infinitely many values thing. Then whatever numbers we're adding up goes there, and we use size in the domain as the weights. And if you're looking at a little interval of values on the x-axis, the size in the domain, the width of that little subinterval is dx. So again, kind of a rip-off of the idea of a weighted average, where we, again, importantly, literally, size in the domain gives you the weights. Okay, now this formula streamlines a little bit. You notice that is just B minus A, a little bit more compact. Go ahead and get that part done. And now we have this more convenient formula for the average value of a function. Okay, and an easy example, this is very plug and chug, very single variable calculus, but you want to know the average value of sine x. Well, that's your f, so that goes there. From 0 to pi, well, 0 to pi gives you the bounds. It also tells you how to find this denominator as the difference. Right, so it's just plug and chug, and y'all can fill in the blanks on doing that computation right there. You get 2 over pi, as it turns out. Okay, everybody buy it? Cool. What if we have a multivariable function? Now, for the moment, still real valued, right? We're going to be looking at the values. Those are real numbers. In this case, we're looking at here. But multivariable in the sense that these values are spread out over a two-dimensional domain. Well, it's no problem. Whoops. No problem. You can do all the same ideas. There's our general form. Again, size in the domain, now being two-dimensional. Now size in the domain is areas. So there's size in the domain as our weights, in the spots where weights go in the weighted average. And same thing, right? Same basic idea. And again, a nice convenient streamlining that denominator, just area of your domain, and so nice and efficient to get that already done as well. So let's talk about an example of this. If I want to compute the average value of x squared, that is then the function that I'm going to be averaging. So x squared goes there. I'm interested in what's happening on the unit disk. Okay, so that's my domain. That's the thing whose area is this denominator. And now I have myself an integral and yada, yada, yada. Details y'all can check for yourselves. Good exercise. Make sure you can do this. It's just polar coordinates, right? But working out that integral in polar coordinates ends up being the most convenient way to do it. And your answer, surprisingly convenient answer, is just 1/4, as it turns out. Does everybody see how I implemented the formula here? Questions? Is everybody happy? Okay. All right. Okay, so among other applications of the idea of the average value of a function, turns out the idea of center of mass actually makes loads of sense from the point of view of weighted averages. I think this is a lovely take, and that is center of mass is the weighted average of position. It's so crisp, it's so succinct, right? So what I'm going to do here, I'm going to write down a weighted average of position, and then I'm going to try to persuade you that center of mass is a reasonable term after the fact. So let me momentarily kind of erase that. Let's just talk about weighted average of position. In particular, we're going to imagine a couple of masses, one small, one big, at these two different locations, x1 and x2. And how would I compute the weighted average of position? Well, the weighted average of position, here's how you do weighted averages. There's only two pieces in this little starter problem, and if there's only two pieces, there's only two terms to be added, numerator and denominator, so no reason for summation notation. We're literally doing a weighted average of position. Those are the numbers we're averaging. We're going to use mass as the weights, of course, right? Seems like a reasonable choice anyway. So the weights go in the usual place. This is just our regular old formula for weighted average, and that value, details I'm going to leave to y'all to think through, but that value is, as it turns out, that's the balance point. That's the point where you would put your finger if you wanted it to balance on the tip of your finger, kind of. I'm going to drop an expensive stylus here if I'm not careful. There you go. Right? Balance point. Now, why does something balance? It balances because the torques offset each other. So if you think about how you would put let me get rid of all this nonsense. If you think about how much torque would this first piece of mass generate, well, it would make a torque, I'm going to say clockwise, because downward when you're on the right hand side is a clockwise sort of a rotational sort of force, right? And then on the other side, downward, when you're on the left side, well, that's kind of counterclockwise, and it turns out that this is a perfectly balanced, in other words, these torques are actually perfectly offset, and that involves some arithmetic to confirm that works out, and I think it's a good exercise. Suit yourself, you don't have to do it, but I think it's somewhat satisfying. Compute these two different torques, add them up, you'll get 0. So I think that's a pretty reasonable take on why we should call this the center of mass, because that's the center point, if you will. That's where you should put your finger, and it's kind of going to balance like you would imagine something called center kind of ought to do. So how are we doing with that? Does that all make sense? All right. Okay, so motivated by that observation, the general version of this, here we did it for just two masses, discrete case, fairly simple. That generalizes to this right there. So if you have a distribution of mass, it's still a weighted average. The masses are the weights. Weighted average of position. Position now, if we're talking about mass distributed in space, position is now a vector location, right? That's literally weighted average of position. And of course, again, we've seen this a couple times before. You can simplify that denominator pretty easily. It's just a total mass. And so here is a nice streamlined formula for center of mass. Now, there is something weird about what we've written down here. You might have already kind of had some, creepy feeling, right, from what we've got written there. This is, I think, the first time we've written down the following, and that is we have an integral where the integrand is a vector. What's that? We haven't defined that. It's not clear that that makes sense, right? I mean, can you just do that? Is that okay? Valid concern, right? It's good to be concerned about these sort of things. Don't let me just, pull a fast one on you, right? Keep me honest, right? Turns out this is actually perfectly fine. There's no problem with this at all. And here's what I think is a nice, natural way to think about it. If I were going to try to make sense out of this, the first thing I'm going to do is multiply that vector by a scalar. How do we multiply vectors by scalars? Well, one coordinate at a time, totally independently of each other. Okay. The next thing, we'd be adding up a bunch of stuff. How do we add up vectors? One coordinate at a time, totally independent of each other. And then lastly, how do we multiply by another scalar? One coordinate at a time, totally independent of each other. And so the nice punchline is, yeah, that's kind of creepy at first glance, but all you have to do is say, yeah, just compute that one coordinate at a time. So for example, this represents the first coordinate of this scary looking expression. It's going to be a vector, and here's the formula for its first coordinate. And there's nothing scary about that formula. That's just a regular old, plain old, real value double integral. Nothing creepy. And then likewise for all of the coordinates, and finally the last coordinate would be this. Okay. So, yeah, in practice, the way we compute coordinates of a center of mass is we compute the coordinates separately. For example, here we have a two-dimensional region, and we're going to compute the x-coordinate and the y-coordinate of the center of mass, totally independent of each other, totally separately, just copying the formulas from up here. So that gives that one, and that gives that one. Everybody happy? Okay, now let's think about, kind of blew past the details of the setup of this. Let's think that through. Our domain here is the upper half disk, so something like this. That's what we're going to compute the center of mass of. The radius is A. Okay, so that's given. Mass is distributed through there. This could be not a constant, but for the purposes of this example, let's keep it streamlined, have the density be 1, no problem. And so let's think now about how to actually compute this stuff. How would I go about computing this integral right here? And I think this is actually a really nice example of an observation that I've made to y'all in the past, which is that sometimes you can compute stuff by symmetry. It's totally awesome. And again, 20% of my physics major pretty much was, oh yeah, that's 0 by symmetry, right? So gotta love that. I mean, it's wonderful to be able to just, wave a magic wand and make what would otherwise be lots of work just disappear into a puff of smoke right before your very eyes, right? Totally awesome. But it didn't announce itself as such, did it? Right? We wrote down this formula, right? That formula is from the formula above. It didn't say, by the way, it's going to be 0 in the following circumstances, because there's too many circumstances. They can't do that, right? So y'all have to take this as part of your procedures, right? Part of how to, when you approach an integral, my advice, always, every single integral that you ever look at, take a fraction of a second. Think about what the domain is, and the domain in this case is, again, it's this upper half disk, it's this thing here. And just ask yourself, do I see any obvious possibilities? Right? There's details to be checked. You can't work through all the details. But do I see any hope, any candidate of a possibility of a symmetry argument? And I sure do there. Look at that, right? This half disk leaps off the page at you that it's symmetric over that y-axis. And that gives you hope. There's the possibility that this might work out, and I claim that it does, and it'd be a great little practice problem to think through. How would you fill in those details? Everybody on board with that? So the lesson here, keep your eyes open, always head on a swivel. The very first thing, honest to God, when I look at a double integral, basically every time I look at a double integral, I just glance and look, is there any hope? Most of the time, there's not. It's not symmetric in any sense. Okay, it cost me a second and a half to eliminate that possibility, but every so often, one time out of 5, we score. Okay. All right. Okay, the other thing I wanted to talk about is the second integral. Now, by the way, let me recognize, to be fair, that's got the same domain. That integral, its domain is symmetric over the y-axis also. It is worth entertaining the possibility of, might that be susceptible to a symmetry argument also? And the answer there just happens to be no, right? And you just got to think through the details on it. Sometimes you can eliminate these possibilities very quickly. I like to make the observation that, as I've made in the past, that this integrand, y, is clearly positive everywhere in this domain. There's no hope for a symmetry argument because there's no hope for my integrand ever being negative. And if your integrand's never negative, then there's no way there's going to be a cancellation. Right? It's not possible. So I don't even have to think through whether it's odd. It can't be odd by this geometric observation. Okay. All right, so we're going to have to do this the old-fashioned way, and here's your two different options. You can do it this way, you can do it that way. It's a question of which way you slice. I have given y'all some guidelines, nothing strict, right? But just, rules that will tend to guide you in good directions. And you remember my two guidelines that I've given you are, try not to slice through corners, and try to make good decisions about what you're going to set yourself up for having to solve for in terms of what else. And sadly, neither one of those guidelines is helpful in this case because neither slicing slices you through any corners. And the only thing where I would have to solve for anything in terms of anything is x squared plus y squared equals a squared, and x and y are equally easy to solve for. So it at a glance kind of appears that this is a sort of a wash. And take your pick, who cares? We don't know how to distinguish based on those two rules. So that said, in this case, one of these integrals is definitely easier than the other. And having them both on the page looking at us here, I can point out why one of them is easier than the other. And that is down here in the second one. Check it out. Our very first thing we're going to do is, in taking that first that inside antiderivative, we're going to have a y squared pop up. That square will cancel with the square root. Poof! All the ugliness just disappeared. This integral is an easy evaluation of polynomials. World's easiest integrals. That's nice. So how did I notice that? Sadly, I noticed it only after having written down the iterated integral. This particular little consideration, you do have to kind of look at them both, and you got to kind of have them both written down at least enough to kind of be able to anticipate what's going to happen down the road of the calculation. So this isn't as useful as those previous two guidelines I gave you. But when you find yourself with an apparent toss-up, an apparent who cares, slice it either way, notice that sometimes it still might matter, right? And again, hard to see it coming without actually doing a little work in advance. Is everybody on board with this? Does it make sense? Something to look out for? How often does this come up? Maybe not terribly, but often enough I think it's worth knowing what to look for. Okay, next thing, moment of inertia. It's really cool physics. I like physics. But this isn't a physics class. So I'm going to be kind of limited. I see some celebrations in the crowd, yeah. I am going to be kind of limited in how much I go into the physics here because I do want to keep the focus on the math, right? Physics in this class I view as an opportunity. Okay, every so often I want to persuade you that what we're doing is useful, right? But there are some nice opportunities for physics to provide examples that will actually help understand the math. And those are going to be my favorite physics applications in this course. Most of that's going to come up later. So a lot of the setup I'm going to kind of gloss over here. Most of this right here, this is some details. Y'all remember this formula from high school geometry. I take a derivative of both sides, yada, yada, yada. You can think that through if you'd like. What I'm going to point out here is that if you have an axis and if you have some object, and if that object is rotating around the axis like that, in addition to understanding the velocity, or let's call it the speed, I want to think about the magnitude, not the vector. In addition to being able to talk about the speed, there's also this related idea called the angular speed. Angular speed is kind of exactly what it sounds like. Regular speed is a linear notion of distance per unit time. Distance per unit time. So linear notion of where am I, right, per unit time. Angular speed is just angle per unit time instead of distance per unit time. Simple as that. Okay. All right, and they're related by way of these formulas. Okay. All right, so now next question. Let's suppose that I'm looking at something here, and again it's moving with some speed, and if I want to know what is the kinetic energy of that thing, no problem, right? Kinetic energy, 1/2 mv squared, all good, because this is the particle. If I know what the speed is, boom, you plug in formula, high school physics, nothing to it. Okay. All right. Here's where things become a little tricky. What if I don't have a point mass, but I have a large lump of mass? Something like that. So I like to imagine that I've got some thing here, right? I've got a thing, and I'm rotating it around. Let me not do that. I don't want to break the chair, right? But I've got some big, bulky thing, and I'm spinning it around, right? How would I compute the kinetic energy of the chair in that scenario? And here's the problem. This little particle right there is not moving very fast. In one of my revolutions, it only travels a short distance. Whereas this piece of mass right here, I don't even have enough room on the page. It's going to travel a much greater distance in the same amount of time. This little particle of the chair is literally moving at a greater speed. So I can't make any sense at all out of this formula down here, this idea of 1/2 mv squared. Which v? Are you talking about the speed of this point? You're talking about the speed of that point? They're different speeds at different points. There is no single speed that I can plug into this formula. Right? Everybody see the problem? Now, a lot of people would think, I don't know, how about center of mass? Reasonable compromise? You sure? I think you're making that up. Right? Are you sure that's going to work? I don't think that's obvious. Not obvious. Right? So there's a different, better approach to this, and here's what we're going to do instead. We're going to recognize that we can approach this as a multivariable calculus problem. In fact, let me just come down here like this. I'm going to say, look, I've got this great big solid thing, and kinetic energy has the feature that the whole is the sum of the parts. Is that good? Okay. So I've got this, again, large object. I've chopped it up into a bunch of little pieces. Each little piece is actually pretty simple. Each little piece, I can just say 1/2 mv squared, because each little piece is pretty much all at the same location, and therefore pretty much all moving at the same linear speed. So there, on the little pieces, you can totally write down 1/2 mv squared. The mass, of course, is dm, the amount of mass in your little piece. Now, here's where I'm going to say yada, yada, yada. Y'all can read through those details if you want. It's just a matter of kind of keeping track of, what are the little particulars about the relationships between these variables, and that's weeds that are not particularly important to what we're doing, other than, getting to the final answer, of course. But here's what I think is interesting and worth talking about, and that is if you look at this final formula, keep in mind we're computing kinetic energy here. If you compare that final formula with this old formula, the linear formula for kinetic energy, you can notice a couple of things. First of all, it looks very similar structurally. It's 1/2 times something times a speed squared in both cases. Right now, in the top formula, this is linear speed, and in this bottom formula down here, this is angular speed. But said differently, with the understanding that we're viewing everything from kind of a rotational point of view, omega, angular speed, is in the angular context playing the role that linear speed played in the above formula. Right? So these are playing analogous roles. And so I'm going to call angular speed the angular analog of speed. And so along those same lines, I think this is a pretty easy pitch. Notice that this thing, whatever that is, we'll come back to that in a moment. The thing that the I here, that's the thing that's kind of playing the role that mass played in the above linear formula. It's an angular analog of mass. And I think this is a fantastic way to think about this object that we're about to give a name and an expression for. It's playing the role that mass played in the above formula. So angular analog of mass. So all together then, and let me get rid of all this distraction stuff here now. Get rid of all of this. I, which was just a placeholder that we gave for this expression, is called moment of inertia. And this is the way to think about it. Again, my opinion, moment of inertia. We care about moment of inertia because it is an angular analog of mass when it comes to kinetic energy calculations. Everybody buy it? Okay. Now, that was a little bit of physics, to be fair, right? So let me streamline that for you. What do you need to know in Math219, not a physics class? What do you need to know about moment of inertia? You need to know this name, and you need to know this formula. And that's all we need to do with it. Okay, now the last thing I will point out, there is a little subtlety to this formula, and that is this R. Let me remind you where that R comes from. It comes from up here, where we're looking at little pieces of mass, right, that are rotating around an axis, and there is a distance between the axis and the point where the mass is that's rotating around. Right? So that's what we mean by R. It's, in fact, I can draw it here too. It is the distance from wherever you're looking to the axis of rotation. Now you're going to notice that I drew this axis deliberately tilted. I didn't draw it as being vertical. That means that this R right here is not necessarily the z-axis. You can't assume that the axis is going to be the z-axis, and so that means this R is not necessarily going to be the cylindrical coordinate R that you might expect because it's called R. Unfortunately, there's only so many letters in the alphabet, and there's a tendency for people to like to reuse them for different purposes in different situations. R gets used for a lot of different purposes in a lot of situations. So in this formula down here, this R is not to be assumed to be the cylindrical R. So here's a couple of versions of what R might be, and I'm going to start with the one where it is. The z-axis that we're rotating around, distance to the z-axis is computed by a pretty simple formula, and yeah, in that case, it's literally your cylindrical R. That's nice, and you do get lucky sometimes. Here's another situation, though. Let's take this line right here. Horizontal line parallel to the x-axis, defined by certain values of y and z. Right? That line, if I want to know what is the distance from x, y, z to that line, it's a totally different geometry, totally different calculation, and you get a totally different formula. Right? And if you treat this as if it's the cylindrical coordinate R, it's dramatically wrong, complete misinterpretation of the formula. Is that cool? Everybody happy? Various different circumstances, and you gotta kind of deal with every circumstance separately. Some students do try to write down a enumerated complete list of all possible scenarios and then memorize the formula for R in all those scenarios. I think it's a really bad idea. For one thing, you're just straight up not going to remember all those formulas forever. You just won't. There's no way. Right? Second of all, there aren't enough different sort of versions of the formula to actually be able to document all possibilities. There's too many different cases. Right? So if you take the I'm going to enumerate and memorize strategy, you'll have an incomplete list that you will not retain. And it's just, like I said, I think it's a really bad idea. What I encourage you to do to address this is what I do, is to look at every instance of a calculation of this sort as a separate little geometry problem in which every single time you're going to have to identify what your axis is and find the corresponding formula. Fresh every time. That is a perfectly sustainable strategy. So here's an example of that in action. We have the following region here, right, in which mass is distributed according to this density formula. Note it's not a constant. So this is a weird distribution of density. It's sort of more dense on the left and more dense on the right, but less dense in the middle. This is strange, right? And we want to find the moment of inertia, it says, but specifically moment of inertia as it rotates around the x-axis. So we got to imagine that this is kind of rotating through space. This looks like a two-dimensional problem. It's kind of sort of a three-dimensional problem in the sense that it's rotating around the line through the third dimension. Right? Everybody see that? Alrighty, let's start writing stuff down. First thing we write down when they say moment of inertia, always write down integral r squared dm. That's always the formula. It's super handy. Now, a couple of little tweaks you do have to recognize. This being, as it is, a two-dimensional domain, makes this a double integral. We're only adding up over 2 dimensions, not 3. So this is just a double integral. It's always integral r squared dm, but the nature of the integral depends on the nature of the domain. Okay. Alrighty. And that allows us to actually write down quite a bit. Mass is density times area. Density is given. So my dm simplifies like that. All right, now we got to figure out what the deal with r is. Again, every time you got to consider it a whole separate little geometry problem. And in this case, r in the integral here, that's distance to my axis of rotation, which is the x-axis. And that distance is like this. And if this is the point x comma y, that distance, it's y. Right? So again, I didn't memorize that. I drew the picture. I understood the picture. I inferred correctly that r here is y. Yes?
Sorry, could you please repeat that part with r equals y?
Yeah, so right, so this is the point x comma y. That's x comma y. That means that that's x. And what I care about here, what I'm looking for, the distance to the axis of rotation is what r is, and it's y.
Okay.
Yeah. Yep. Yeah. Okay. There we go. Good. Okay. Yeah. So, and then integral follows, and I am going to point out. Oh, and I guess I should recognize this domain gives me these bounds. This is one of the situations where the order of the slicing matters quite a bit. It would be quite a bit uglier bounds if you were to do this the other way. So you 100% want to do this as dy dx. You then have to compute the integral, and there's some single variable calculus that comes up in the sense that this inside integral simplifies like this, and that means that your outside integral has some of those annoying, what's the little clever trick on these single variable integrals that you just have to make sure you just got to remember what those little tricks are. Right? So make sure you're good with that. There's no getting around the fact that single variable calculus continues to be useful in the multivariable calculus class and well beyond. For whatever it's worth, for your consideration, the engineering school has specifically requested, I'll say forcefully requested, that we continue to make sure that students are challenged with single variable integrals, because there was a few years, many years ago, where we kind of let up on that. And what they were finding is that there were senior engineering majors that had completely forgotten how to do single variable calculus. And they considered that to be an unacceptable state of affairs. So this comes down from the engineering school. Don't blame me, right? But you do need to make sure that you're still good with integrals. And so, for example, make sure that you are solid with how to do an integral like this. Okay. All right. And we're done with Chapter 5. How about that? And we're going to move along now to Chapter 6. Now, reminder, we are proceeding along well past the Exam 2 fair game material. Right? So the stuff that we're doing here is not fair game for Exam 2, but it is fair game for Exam 3 in the final, and again, that's coming up pretty soon. So we gotta keep covering territory here. Okay. Here's an observation about every integral we've seen so far. We've seen 3 kinds of integrals so far. We've seen single variable integrals, double integrals, triple integrals. Now we've also seen various, what I'm going to call integration techniques, right? Change of variables is not a new kind of integral, it's just a technique. Polar coordinate integrals sounds like it's a different kind of integral, but it's not. It's just a technique for computing what we already, off of this list of 3 different kinds of integrals, right? Single, double, triple. That's all we've seen so far. And they all have this common feature, and that is the domains are the same dimension as the world that they live in. So, for example, if you do a double integral, your domain is 2-dimensional. And it is a 2-dimensional region in a 2-dimensional world. Right? So, on the other hand, here's a very reasonable question. If I have a curve like this. And if that is a curve in the plane, the XY plane like that. Now, if this were the, somehow, whatever this would even mean, if this were the domain for an integral, if I wanted to make some accumulation argument, if I wanted to chop it up, add it up, the whole is the sum of the parts on this curve, the curve is one-dimensional. It lives in a plane which is two-dimensional. That's weird. We've never seen that before. We have no preparation as of this moment for how to handle some sort of a, like I say, accumulation on this kind of a domain. And so we're going to have to actually define now a brand new kind of integral. This is integral number 4 for this class. By the way, the final tally is going to be somewhere around 9, if I remember correctly. There's a lot of different kinds of integrals we're going to talk about. So this is number 4. And here's the big idea. The idea is all of our accumulation arguments are where I take my domain, whatever my domain is, I chop it up into little pieces, like so. I'm going to add up over, wrong color. I'm going to add up over all of those pieces. And on each piece, so for example, on this little piece here of size delta S, I'm going to prepare for the possibility, various different kinds of possibilities, but that whatever quantity I'm interested, whatever accumulating quantity I'm interested in, where the whole is the sum of the parts, right? We've got to be able to add these up. But I want that quantity to be expressible as quantity per unit length times length. So a lot like we did in single variable calculus integrals, right? Stuff per unit size times size. We're still totally stealing all of that, sort of strategy from every other kind of integral we've seen in the past. If I have stuff per unit size times size, what I have here in orange gives me stuff. That tells me how much stuff there is on this piece. And then I add up all those little pieces of stuff to get the total amount of stuff. This is very strategic, just kind of broad strokes. You should be wondering at this point, how on earth are we going to compute that? Am I supposed to know how to compute this thing? No, not at all. Not yet. Right? So this is just talking about the strategy of how to take an accumulating quantity, chop it up into little pieces, and argue that the whole is the sum of the parts. That's all we're doing here so far. All right. Okay. So this is a new kind of Riemann sum, aka it's a new kind of integral, and we're going to denote it like this, which I think is pretty believable notation, right? We represent deltas with differentials, we represent limits of sums with the integral symbol, and whatever this stuff per unit size is, that is our integrand. So copying notations that we've used in the past. So this, by the way, is called a scalar line integral. It's a little bit of an odd term. I think the integral part of this is pretty believable. After all, it's a Riemann sum. Of course, it's an integral. Okay, fine. Let's not go back into that again. Why do we call it a line integral? That's pretty strange. The answer is that in some contexts, the word line doesn't necessarily mean straight line. This is the kind of the short version. So this curve could be called a curved line, if you will. Y'all probably heard the term a line drawing. Have y'all heard of line drawings? They're not all straight lines. Right? So this is kind of a flexible interpretation of the word line. Sometimes, by the way, these are called path integrals. That kind of addresses this awkwardness. I think that's nice. I wish they were called curve integrals. It's too late for that. Okay. What is weird, and we'll draw the line in just a moment here, no pun intended. Why do we call this scalar line integral? That's seemingly unnecessary. And the answer is, it turns out there's another kind of line integral that we're going to see next week. it's very hard to see this coming. Don't try to imagine what this other kind of line integral is going to be. It's really not obvious. But to distinguish it from that other thing, scalar is a reference to the fact that the differential and the integrand are both scalars. And as you might suspect, the new kind of line integral we're going to see next week, these are not scalars. And it's weird. But it comes up very naturally and it's very useful. Okay, we'll draw the line right there. See y'all later. Good luck on the exam on Friday. See you then. Don't forget about attendance. 2 seconds.